what I thought was going to happen in this position, and what I then thought, so who I thought was going to win, who I then thought was going to win after one step, looks at the error between those, adjusts the neural network weights a little bit in the direction to correct that error, to make these predictions self-consistent. And perhaps surprisingly, it just used greedy policy improvement. It just picks the action that maximized from white's point of view and minimized from black's point of view, and it never explored. And yet, they're always converged in practice, despite all these issues we hear about neural networks possibly being unstable with RL, and these question marks about exploration. It always converged to a very effective solution. So can anyone think why this might be the case? Like, why didn't it need to explore? Yeah?
Is it because the dice roll introduces some randomness into it, so it gets into states it might not have
Right.
expected?
So backgammon has dice in it. Backgammon's got stochasticity. And so that means that there's inherently a lot of exploration of the state space. So even if you don't explicitly explore, you still get to see everything. You still get to see all of the different states. And so in this kind of situation, it's not strictly necessary to explore. Can anyone think why it might have been stable when, well, let me tell you that this is not true for other games, that actually in other games that people were very excited after this and they tried the same ideas in checkers and chess and Othello and all these things, and every time it diverged and it failed to work. So can anyone think what was special about backgammon that meant that this idea worked so well? Yeah.
I guess the number of states is quite small. The number of actions you can take at any when you're in any state is quite small as well, because you only have 2 moves you can make with the dice roll.
It's actually got quite a big state space and quite a big action space. So in backgammon, I mean, you've got 2 dice, and the 2 dice you can move your counters any number of steps according to the 2 dice, and so there's a branching factor for the dice and a branching factor for what you do based on those dice. And there's a lot of states in backgammon, I think, something like 10 to the 40-ish. Now, the answer is actually the same as the previous answer. It's because of the dice. So the dice, the stochasticity in backgammon smooths out the value function. So because you've got randomness, although there are tactics in the game, they're kind of smooth tactics because you don't exactly know what the dice are going to do after this. So there's some randomness of what might happen next and how your opponent might respond after that. And all of this randomness has the effect of smoothing out the value function because you can't precisely rely on taking one particular line and your opponent responding in one particular way and then you responding in one particular way to that, because the dice don't let you. Right? Any random event might happen. That smooths out the value function. So backgammon has a very smooth value function which suited neural networks and made them much more stable in the presence of value function approximation. Whereas when people tried to use this in more precisely deterministic games like chess and checkers, it didn't work. And I think you would now need to reconsider this in the light of the recent methods like DQN and so forth, which might address that. Okay, so how strong was TD Gammon? Well, using this, so this representation here, we can think of as 0 expert knowledge. We really didn't put in any knowledge into that. But you can also add some expert features based on standard ideas of, there's a few standard features you can use in backgammon. So with 0 expert knowledge, TD Gammon, just the neural network, achieved what we call strong intermediate level of play. But if you gave it handcrafted features, it reached a more advanced level of play. And then if you combined handcrafted features with a 2-ply minimax search, it achieved strong master level play. And then with a 3-ply minimax search, it achieved superhuman play. So even in backgammon, with this very powerful neural network, at that time it was necessary to actually use a minimax search on top of this value function. So you take this value function, you perform the minimax search, and you use the value function at the leaves, just as we suggested earlier. But this is all a long time ago. So Jerry Tesaro actually went back a few years ago. So this isn't super recent. This is, I think, like 2008. Jerry Tesaro went back to TD Gammon and said, well, what would happen if you just ran out these neural networks, trained them for longer using better hardware? This isn't even using GPUs or some of the things which people know. You could probably get three orders of magnitude more computation than this used. But all he tried was to continue training using just the raw features with 0 knowledge at all. And the different colors here basically show how many hidden nodes the network had, whether it had 10, 20, 40, or 80 hidden nodes in a simple multi-layer perceptron feed-forward network, vanilla neural network. This is the number of self-play training games, up to about 10 million. And this is the performance against a standard evaluation benchmark. And what happened was, if you just kept training this thing, it got better and better and better, and in the end it massively outperformed the version with the expert features. So the story was basically that although expert features were used a little bit in the original TD Gammon, that was just because there wasn't enough computation available. And so now this version here, this magenta one, achieves superhuman level of play with literally zero human knowledge. So it's a nice idea. You literally have a program, plays itself, builds up a neural network that estimates who's going to win in this position, does a little bit of look ahead using that neural network, and you've got superhuman game player. Yeah, question?
Are there ways of reading out the features that this program learned to train the human players?
Okay, so that's a great question. So what happened in backgammon, and it's also happened in some other games, is that it completely changed the way that humans play. So humans then started to look at how TD Gammon played. They're like, oh, I didn't even know you could play backgammon like that. And they discovered new strategies and they started to figure out different ways to play better. So human level increased as a result of this. Not by reading out the features, but observing the way it played at the end of the network. So in general with neural nets, it's hard to interpret the intermediate stages. You can look at it a little bit and try and tease it apart, but I think ultimately humans learn by just watching the way it played and saying, that's a good way to play the game, realizing that this is a good way to play. Okay. So is that clear? So far we've looked at how to do self-play reinforcement learning to achieve high performance in certain classic board games. And now really we're going to focus on how to get a more sophisticated mixture of reinforcement learning and search. Okay, so let's start with sort of the most familiar method. Let's start with basic TD. I'll call it the simple TD algorithm. And let's see if we can understand how to do better than simple TD when we know that we're using a look-ahead search. And so we can think of standard TD as looking a little bit like this. That at every stage, we basically have some value function with parameters W. That's our value function estimating who's going to win the game. And the value function at one step gets updated towards the value function at the next step. That's what this arrow means. It's like a backup. It basically means that we look at the value function here, and this arrow means we use the value function here to improve our estimate of the value function here. So this is like we were in state S1, then I played a move, I ended up in this state S2, and I get a better estimate of the value, and use that estimate as my target to update this guy. So that's standard TD learning. And then what we've looked at in Logistello and TD Gammon so far is it's like this two-stage process where first of all we learned a value function by self-play, and then once we had this value function, we can do a big minimax search tree using that value function at the leaves. But that isn't necessarily the best way to combine minimax search with reinforcement learning because it's not helping us find a better value function. The search isn't helping us figure out the value function. We're only, it's like we first of all do our TD learning and then later we do the search. And the question is, can we actually make use of search to make our value function better in the first place? So that during the process of learning, we actually figure out a more effective value function. So simple TD by itself actually has performed well in some games. So we saw in Logistello, TD Gammon, there are cases where it did very well. But there are also games where it does very poorly. So chess and checkers in particular, people spent a lot of time trying to figure this out, and they discovered that TD by itself, back then, who knows if this is still true using more sophisticated function approximators, at least back then, it performed poorly in these quite tactical games. And so, why is this? And I think the answer is it's about the tactical nature of those games, that you really need some kind of search to be able to even figure out the signal and the position. If you just have your features that tell you, how many rooks and bishops do I have in this position, it's not enough information to figure out the precise tactics that lead you to a checkmate. You just can't find checkmates in this game. You can't find the specific tactics that you need to follow to capture someone's piece or to pin them or to do a fork, whatever it is. You need search to estimate the values more accurately. And so the goal is to learn directly from these minimax search values so that we really have this rich search information inherently as part of the learning algorithm. And so can we do this? And the answer is yes. And again, this dates back a very long time. So I'm going to introduce the oldest version first, which is now I call TD root. And so this idea is, the idea is basically to say we're going to update the value towards our successor search value. So in other words, what we're going to do is when we do our TD update, instead of updating our value function towards the value function at the next state, what we're going to do is update our value function towards our more accurate value function that we got by doing a search. So in other words, if we're in state st here, what we're going to do is we're going to take a step, we're going to run our really big minimax search, really figure out what the right move is, you know, is there some checkmate available here or not? And then once we've got that much richer value function, we're going to use that as the target to update our original value function. So the reason the arrow comes from here instead of from the top is to basically to indicate the fact that once you've run this big search, because it's a deterministic game, once you've run this big search, there's one particular leaf node that actually is on the principal variation. There's one leaf node that was the minimizing, maximizing leaf node, the one which contributed all its value and propagated all the way back to the top. There's one leaf node which is the one that we basically picked out of all those leaf nodes. And that's the one that we used. That value is the one that basically, it's the same as, this value has the same value as the whole search. There's one leaf value that contributed to the eventual value of the whole search tree. And that value is the one that we back up to the root node here. So basically, the right way to think of this is we update our value function towards the outcome of a deep search. That, you know, I'm in this position, I think the black's going to win. Then I take a step, I do a really deep search, and I discover that white's going to win. And so now I'm back here, I say, oh, well, I really wish I could have figured out without doing any search at all that white was going to win. And that would be a very nice value function to have if we just knew without doing any search that white was going to win. So we're always, you do the deep search, you figure out what you now believe, you get those results and you back them up. Okay? Is that clear? Okay, so that's the TD root idea. So this was introduced by Arthur Samuel back in 1959, and it was the first ever TD learning algorithm. And he applied this in checkers using self-play, and it learned to defeat an amateur human player, which was a big deal at the time, although it's not clear how strong it actually was. So this was great, but it also had some other ideas in there which kind of we now think are a little odd. So it was a bit conflated with all these good ideas about TD and this TD root idea and minimax search. Those are all in there and good, but there were some other funny things that meant it was not quite the vanilla thing. But nevertheless, I think we should attribute all of this good ideas to Samuel. But then, people have taken these ideas and they've progressed them since then. So the first progression is an idea that's called TD leaf. So this idea really has been successful in chess and checkers, so it's worth understanding. And the idea of TD leaf is to basically say, instead of just updating the value now towards the search value of the next step, let's run a whole search now. We want the whole outcome of my search to be made more accurate. So the idea is that at time st, we're going to run our search. What we'd like is we'd like that whole search to end up giving to output a value which is the same as the value that we got when we did a search at the next step. In other words, if I'm in a position, I run my big search and I think that black is winning, then I take a step, I run another big search and discover that white's winning, then we want to change the whole of this search procedure to say, actually, oh, I got it wrong, maybe I should change the whole of this search to have given a different outcome. We don't just change the value function, we change the whole of the search to give the right answer. And again, the way we do that is we only need to look at the leaf values. There's one leaf in each search which contributed all of the value to the eventual outcome of that search. And that's the only one we need to update. So we update this leaf node here, which was on the principal variation from st. That's the leaf that contributed, that's the one we chose. We chose this leaf, we chose all these actions down to here, and then this leaf. And all we need to do is to basically update the value of this leaf towards the value of this leaf here, which is the principal leaf that we actually chose at the next time step. In other words, if this value had been a little bit higher, it would have made our whole search value a little bit higher. And so if we ended up underestimating the value, we discovered that our value was a bit higher, we want to change our whole search to be pushed up, and the way we do that is to push up the node that we're actually picking right now a little bit. So that's TD leaf. Yeah, question?
Can I question, because
still a little bit confused.
Yeah, good.
What's the difference between like research for the like this search, for the case we are in the ST state and ST+1 state? Because I
Yeah.
see that there must be some differences.
Okay, so let me try and explain this clearly. So we're in some state ST, that's our current position. We run a search from this state. What this diagram indicates is what we ended up picking as a result of that search. So as a result of that
This is
search,
like full search, right? We are going for all the.
we did a full width search. At the end of that full width search, we ended up deciding that this red node was the best one. And then, white decided to move to this red node and black decided to move to this blue node. That's what we decided at the end of that search. Then we actually took a real step. We played a real move in the game. We ran another search. So we start now from this red node. We're in a new position. We kind of can share that we've moved on to that red position now. We run a search from that red position. And now we find a new principal variation. So now we run a search and we again decide that we're still going to move to the red position, we're still going to take this one leading to the blue, and then we're going to take this move leading to the green. So what we can do is we can basically say, we want the outcome of this whole search to be moved a little bit toward the outcome of this whole search. So how do we do that? Well, we can say, well, the value which determined my outcome here is exactly the value of this blue node here. The value which determined my search tree here is exactly the value of this green guy here. So all we need to do is to update my value function of this leaf here towards the value function of this leaf here, and that will make my whole search more like the search at the next step. Good, more questions. I know this is confusing, so it's good to get questions.
So what happens at the T+1 step if you decide, when you look at all the 4 lowest nodes, that actually you didn't want to take that blue step, you wanted to go into the other
That would be fine.
direction?
That would be fine. So if you actually went a different way,
Yeah.
and this ended up being your node, now we would say, okay, well we've got some new search over here, which has some new principal variation, and we ended up deciding to go there, then there. And so this would then be the node which contributes the value to this whole search tree. This is the minimax value. So the minimax value of this whole search is equal to our value function here, because that's the one we chose. We were minimizing and maximizing all the way down to this point. So now all we would do is update our value of this node here towards the value of this node here. And that's equivalent to saying that we're going to change the whole of our search from this route towards the whole of the search from this successor route. The plus here means that we're doing some search. So what this is,
So you update the blue one on the left, even though you didn't take the blue one
yes,
on the right.
because we want to know how could I have made, this was the way that I was searching in this step, and I want to make the way I was searching in this step better. I want to make it more like the way I was searching on the right step. And the only way you can do that, because currently you're in a situation where you're picking this. And so the only way to change that, the only way you can affect this, like if you think about an incremental change, you just get to change things a tiny bit. If you change any of these guys just like a fraction, it's not going to change the minimax value, because these aren't the ones you're picking at the moment. Like if you change any of these other values, it's not going to change. Like if you change this one, even though it's the one you picked at the next time step, this isn't the one that you're picking right now. So right now you picked this guy. So if you want to make the value of this search tree higher, you need to make this particular value higher a little bit. Now at a certain point you'll cross a threshold where suddenly a different node will become better or worse. And at that point you then change that node. But you're always just changing the node which is contributing to the minimax value.
So if my value function for the blue node gets lower, and other nodes from this lower level would become better, then I can't have to because I try to remember all the nodes I visited, so I can easily is my problem?
No.
Okay. So if for the blue node, I found that I need to lower the value function,
Yes.
and actually from this first search on ST3, I would find that another node would be better after the update, the blue node.
Right.
So how can I know which was the better?
Okay.
I
So,
don't want to
so the question is that we do one update that changes what the principal leaf is to say this one, and now you want to know what do we do in that new situation. Do we need to remember that we used to go to this one? The answer is no, you don't care. Like, you only look at what you're picking right now. So if we update our weights such that now if we search from ST, we're picking this guy, we don't need to remember what we did before, because we're now in a situation where when we run this search, we're picking this guy. So if we're in a situation where we're running a search tree, and this is the principal leaf that's contributing its value, again, we just push up or down the value here a little bit. So it's a bit like just think of this as a function approximator that has some non-differentiable boundaries in it. So you've got some function, which is like a linear function approximator, which is like a piecewise linear function approximator. So you can think of this whole search tree as a piecewise linear function approximator. Okay? So it's doing this minimax, you get this piecewise linear function approximator, and you use that piecewise linear function as an estimate of the value function. You want to update your piecewise linear value function towards the piecewise linear value function here, and the only bit you need to look at is the piece you're in right now. You don't need to look at all the other pieces. If you get pushed over a boundary between one piece and another piece, okay, so now you're in this other piece, and now you just adjust yourself a little bit on that one. So there is some non-differentiability here, which you need to be careful about. So you might worry that you get trapped in some local optimum or something, which I think is your concern. But it turns out in practice that this is quite effective, for the same reasons that you have a rich space with stochastic data and you're dealing with all these maxes. So we see the same thing in deep learning, methods like MaxOut, where you can have these rich, non-differentiable function approximators with hard non-linearities in there, and yet you can learn very effectively to achieve some, to optimize in this space, because you're seeing every single state you visit in each game is going to take you to, going to make different decisions at these boundaries. I think your concern is something about local optimality.
Maybe.
Maybe, okay. All right. I'm going to try and move on, I think. Are people roughly okay with this? There's a slide there, you can come back to it. Notation basically means the plus indicates running a search from this node onwards, and this L plus basically tells us which leaf we've chosen, the principal leaf. So the principal leaf from that route is this L plus, if you choose to come back to us. Okay, so that's TD leaf. So TD leaf worked quite effectively. So it was trained in a program called Nightcap against an expert opponent. And the only knowledge it was given were the piece values. So it had a fairly large number of different features. Like this, again, it had this binary linear value function. Had a fairly large number of features, but it was only told the weights of some of them. It was told the weights of the piece values. It was told a rook's worth 5, a bishop's worth 3, etc. And then it learned all the other weights using TD leaf. And indeed, it was able to tune the piece values afterwards, but it was initialized to having some knowledge so that it could get off the ground and do something interesting. And then search, it used a standard minimax search with all the usual standard enhancements. And the results were that it actually achieved master level play after a relatively small number of games. But there were a couple of caveats in terms of how it worked, which was it wasn't effective when it played by self-play. It actually had to train against an expert opponent. And it also wasn't effective when it was started with randomized initial weights for the piece values. It needed to get off the ground first. So we actually went back to this a few years ago, and we came up with what we considered a better method that addressed these problems. But before I do that, I should say that TD leaf was also applied to Chinook. If we go back to this checkers playing program, Chinook, which was the program which eventually went on to achieve perfect play. But before it achieved perfect play, so Jonathan Schaefer and others went back to Chinook and tried to say, well, instead of hand-tuning the weights, could we have done better by self-play reinforcement learning? And so they used TD leaf to adjust the weights. And again, they kept one material weight fixed, like the value of a checker, they kept fixed to kind of anchor the whole thing and keep it stable. But what they discovered was when they did this, and they just played this thing by self-play and adapted the weights using TD leaf, that the self-play weights that they learned did even better than the original hand-tuned weights. So again, this was when it was already playing at superhuman level. So this shows that TD leaf is able to achieve superhuman level in checkers. Okay, but there are these caveats. We want to be able to do more by self-play. We want these algorithms to be more robust and more efficient to learn. And so we introduced a method called TreeStrat, a few years ago, so with Joel Vaness and others. And the idea here was to interact with Minimax search in an even richer way. And so the idea was to say, instead of waiting a step and looking at a search that you run after one real step, why mix real and imaginary steps? Let's just do everything in imagination. Let's start from, we're in some position, let's run our big search tree, and let's just look at that search tree and update our value function from the information within that search tree itself. So you only need one search tree now. But what we do is that we basically want to have the following idea, which we want to update the value of every single node in that search tree. We want to basically say, we want the value function of that node to predict what a deep search would have done from that node onwards. So if we can get the value, if we can estimate the value of each node, for example this one, correctly without doing any search, then we think we've got a very good value function. So the idea is that every single node of this search tree, we update the node here towards the search value from that node onwards. And we update the node here, the value of this node here, towards the search value from that node onwards. And we do that for every single subtree within the whole search tree. We basically say we want the value function to correctly predict what the whole search would have done from that node onwards. And we've got this very rich data. Every single time you run a search, you generate millions of minimax values. So the idea was to use those minimax values effectively rather than just taking one value and throwing away the rest of the search, as we did in td-leaf and td-root, where we generated this whole search, but we only used one value from each search. So in td-tree, in treestrap, we use all of the information from the search as targets to make the values better at every single node in the search. Is that clear? I'm getting more nods for this one. Is this less confusing than td-leaf? Okay. This method is quite effective. So the program that Joel tried it in was called Leap. This is a binary linear value function again, using around 2,000 features. These were handcrafted features. But they started with completely random initial weights, so we didn't give any information about the piece values. And then adjusted those weights by treestrap. And after adjusting the weights by treestrap, we then played it on the standard online chess server to see how it played. It won 13 out of 15 games it played against international masters. So this, I think, is it's also been used, I believe, in some. So the chess programming world is very closed shop, but we at least heard from one of the strongest programs to say they've got much better results in chess than this using treestrap. So I think it's a method that can go further. But it was effective in self-play and effective in random initial weights. And the reason that it tends to be more effective is because it doesn't have this mixed backup, wherein these previous methods, you're kind of mixing between doing this big search yourself by kind of imagining what would happen, and then looking at some sampled action, some random action that was taken in self-play, and mixing these two types of backups together isn't necessarily the best idea. So in treestrap, we just do something simpler, which is to generate a big search, update the search from the search itself. So update a shallow search from a deeper search. That's the way to understand it. You want your shallow search to give you the results the deep search would have done, with less computation. And the limit of that is you want your value function to directly give you the results the deep search would have given you without doing any search at all. Okay. Right. So, that's the end of that sort of mini section. Any questions on those? Successfully confused everyone in the room with the TD-leaf. Yeah.
Sorry, so you never mentioned anything about convergence. Is there any kind, or did you deliberately do that?
So let me say some things about convergence. Okay. So minimax search converges on the minimax value function. If you search deep enough, it will eventually, if you can get to the end, it will converge on the true minimax value function. Self-play reinforcement learning. I mentioned Michael Littman's seminal work. So he talks about convergence of certain standard RL algorithms, Q-learning and so forth, in the context of table lookup value functions, and shows that these self-play reinforcement learning algorithms do converge to the minimax value function. So that's what we know about convergence. I would say for all of the practical examples we've looked at, we're outside the scope of what is known to converge. And in some cases, we're using methods that we know may diverge, like in TD gammon. We know for a fact that using a neural net with self-play can diverge, and yet it worked in TD gammon. So these methods here, empirically, what's important with all these methods, like this approach here, is that you have to ground it. You can't just learn from your own search without grounding it. You can't just keep running on your own big search tree without seeing any real data. And the way that you ground it is you have to get to the end of the game. You have to interleave this with real outcomes. You have to see some real outcomes in your search tree at some point. Otherwise, you can end up just kidding yourself into believing that you can update your value function towards what you searched it to, and then just keep doing that, and eventually you'll drift away from reality. So you have to have some reality in there, which means you have to do this from all kinds of positions. The route has to be at all different stages of the game, and you have to have sufficient number of positions that actually see the end game, the outcome of the game, to ground this. Okay, that's an empirical concept. Right. So I just want to talk about simulation-based search again. So in the 2 lectures ago, we had a lecture where we talked about simulation-based search. We talked about this idea that we can achieve high-performance search by running simulations and applying RL algorithms to those simulations. And so we had this idea that you can basically start at some root state, like the current position, generate simulations from that root state, apply, say, Monte Carlo learning to the simulations that you run from that root state, and get a very effective high-performance search. And so now what I want to do is just talk about that again in the context of what we've learned about self-play. So in that lecture, we were really mostly talking about single-agent case, but I used the example of Go. And so we've seen that you can do something like run your simulated experience. Now we're going to simulate those games by self-play. So in other words, we're going to start from state ST. We're going to run out games where white plays a move using our policy, black plays a move using our policy, all the way to the end of the game. And we're going to learn from that experience by applying, say, Monte Carlo learning or TD learning or any of the updates we've seen so far. And when we do this with Monte Carlo control, we arrived at an algorithm which we call Monte Carlo tree search. And in the last lecture, we saw how this is very effective in the game of Go. I just want to mention that the most effective variant in games to date has been something called the UCT algorithm. And the UCT algorithm is basically Monte Carlo tree search with, instead of doing something naive like epsilon greedy, it uses a slightly more sophisticated exploration strategy, which is to say at every node in the search tree, it treats as a bandit algorithm and applies the UCB algorithm at every single node in the tree that we saw in the last lecture. So we had this bandit algorithm in the last lecture where you could decide which arm to pull so as to make sure that over time you explore all the different arms in the way that gets you the most money from your machine or whatever it is. And so this idea can also be applied in the Monte Carlo tree search by treating each node in the tree as its own bandit and basically pulling the arm, picking the action, is basically now means selecting the child that is most likely to win the game. And so you basically get to explore all of the children systematically in a way that encourages you to visit the parts that are most successful so far, while still exploring everything. So this basically guarantees that you explore all parts of the tree very, very systematically, but in a way that still gets an awful lot of the simulations go down the principal variation, the best part of the search tree. Okay, that was a little aside. So the UCT algorithm has been very effective in many games. So we saw last lecture Go, there's also games like Hex, Amazons, Lines of Action, these other games which, roughly speaking, any game which has a large branching factor or where it's hard to construct a value function, it turns out that these Monte Carlo tree search can dramatically outperform what was achievable with standard minimax search algorithms like alpha beta. Now, if you take the UCT algorithm, someone asked about convergence, you take this UCB algorithm and you run it, apply it with self-play, this has been proven to converge on the true minimax value for that game. So you start knowing nothing about the game, you just run these simulations, self-play, I guess you know the rules of the game, you run these simulations from your current position, and you learn by self-play, applying your Monte Carlo control, eventually you will find the minimax optimal values in any of these games. And even if you don't reach convergence, you can still get very good performance in many challenging domains. Okay, I just wanted to point out that in many games, you don't even need to do something so sophisticated. So in many games, you can use simple Monte Carlo search, this idea of just running rollouts and picking the best action from those rollouts. So Scrabble and actually backgammon are two examples of this. Scrabble we'll see in a moment. Backgammon, it turns out that the TD Gammon guys, Jerry Tesaro, when they went back to TD Gammon, they discovered that they could do better using Monte Carlo search than using an alpha beta search in backgammon. So that was some later work that they saw. So the final part of the class, I'm going to talk about two imperfect information games, which are Scrabble and poker. Both of them build on Monte Carlo search ideas to achieve success. So basically the part we're dropping is this sort of minimax search via brute force alpha beta kind of depth first search. And instead we're going to consider these self-play approaches to search based on simulation-based search algorithms, Monte Carlo search, Monte Carlo tree search. Okay. Right. So let's consider the game of Scrabble first of all. So in the game of Scrabble, the first program to achieve superhuman performance was a program called Maven. So the idea of Maven, so first of all, I mean, Scrabble actually, you might think that it's trivial to make a computer program that's better than humans because you give it the perfect dictionary and a human could never have a perfect dictionary and therefore anything with a perfect dictionary must outperform humans. Turns out not to be true for two reasons. The first reason is that the top human players memorize the entire dictionary. And the second reason is that not just the entire dictionary, they memorize all the anagrams and all the hooks that you can get from one word to the next one. The second reason is that there's actually a lot of strategy in the game of Scrabble that humans are very good at and naive alpha-beta search or something like this is very poor at. And the strategy basically comes from the fact that you don't just want to greedily play the move that gets you the most score, you want to make sure that you leave letters on your rack after you've played your move that give you the most potential for score later on in the game. So if you leave the blank on your rack, you're probably going to get a bonus 50 points in the next move when you then get a 7-letter word and do even better. So there's a value to keeping things on your rack, which means you can use these good letters, the S and the blank and so forth, to do very well on your next turns. So what Maven did was essentially a reinforcement learning approach. So this is the one game we're going to consider where we won't just look at the outcome of the game, but rewards along the way. So in Scrabble, you basically get a reward along the way, which is the score at every single move. So you play your word down on the board, you get some score, and then you get some immediate score, but you also have a value function, which depends on how good your rack leave is. Technically, it also depends on the board position as well, but Maven ignored that and just said, let's come up with some general values that say, how good is it to leave an S on your rack? How good is it to leave a blank on your rack? How good is it to leave a Q on your rack? All these kind of things, and sort of independently of the actual position. And then what they did, so this is Brian Shepherd a few years ago, what he did was to build a binary linear value function again. And the features this time are like these letters that you leave on the rack. So there'd be one feature saying, have I got a Q in my rack? After I play my move, have I left a Q in my rack? Have I left a Q and a U in my rack? Have I left 3 I's on my rack? These kind of features, and for all 1, 2, and 3 letter combinations. And so, you might naturally consider that leaving a Q by itself on your rack should have a very bad value, but leaving a Q and a U together could have a very good value because it lets you play this high scoring Q. And then, much like Logistello, what Maven did was to learn the weights for this binary linear value function by this policy iteration approach, where it ran batches of self-play games, start with some policy, run a batch of games against itself, evaluate those using Monte Carlo, i.e. regressing to the game outcomes to figure out the value function, and then using that to improve the policy and iterating again and again and again. So it learned this value function, so it's got a value function, and then it used this value function in a search. And the search was the simplest possible Monte Carlo search you can think of, which is just to imagine n steps of self-play. So the idea was to basically, you've got some rack leave, and now you've got the position you're actually in. So what Maven did was, if you want to know how good is it to play this particular word in this particular location, what it did was it would actually, in its mind, it would play that word, and then it would run a bunch of rollouts to see if it just randomly picked letters from the bag and rolled out those the game for some number of steps after that, played for itself, played for its opponent, played for itself again, and played for some number of moves, and then it would evaluate the resulting position by the score for those end steps, plus the value of the rack leave at the end of it. So basically, roll out this position, and then truncate and use the value function after end steps. So it didn't go all the way to the end of the game, just for computational reasons largely. Is that clear, the idea? So basically, rolls out games from this point onwards, considers a move, rolls out, it's like, I could play the word fox over here, so I play fox, I now roll out, say, 100 different games, starting from this position with fox on the board, play 100 different games, see what score I got in those 100 games, take the average of those games, the scores in those games as my estimate of the value of playing fox. So I add up the scores along the way when I play fox, after I play fox, and then truncate the game and use my value function. It also had a specialized endgame search, but I won't go into that here. Okay, so how did it do? So I really like this position here. I think it's a really fun story. So this was the moment when humankind realized that they were defeated at the game of Scrabble, where there was this position getting quite complicated, and this was against the world champion Adam Logan to decide whether the humans or computers reigned supreme. So Adam Logan was the reigning human world champion, and they reached this position where Adam Logan was winning this particular game by miles, and he thought he was had a comfortable win. But it turned out that Maven had basically been rolling out all these simulations, and it figured out they had one chance to win this game, which was to fish for this particular word, which would give it a 50-point bonus by playing out all its letters and complete the game and get all the bonus points you get from finishing the game as well. And it fished for this combination, and it picked up the letter, and it played this word mouthpart, which is a 9-letter word, which means you only get 7 letters in Scrabble, which means it had to play over 2 existing letters. And it fished for this opportunity and saw that this was the only way to win the game. And indeed, it got the word that it fished for, played this game and defeated Adam Logan. And this was one of the games that he used to win the World Championship. I don't even really know what a mouthpart is. I mean, that's Scrabble for you. Anyway, they ran some analysis of this game afterwards with some human experts rolling out different games, playing out amongst all the different possibilities. And they estimated that Maven only made an error rate of 3 points per game. But basically, if you looked at the entire game that Maven played out, and they typically score maybe about 400 or 500 points in a game, that if it had played perfectly throughout that game, it would only have changed its expected score that it could have got by at most 3 points in any one of those games. So it was very, very close to perfect. Caveat, I suspect this result is bogus because I'm pretty sure that actually you can do better than naive rollouts by doing a Monte Carlo tree search and actually looking at the contingencies of what the opponent played and then what would have happened after that. So I suspect a real strong search program, which someone might one day build, would actually do better than what humans currently think is optimal.
So did it not have any sort of concept of trying to avoid leaving the opponent in a position where they could easily get a triple word score or something?
Well, that appears in the rollouts. That appears in the rollout. So if you basically open up a triple word score, like you play Fox, and it gets you a big score, but it leaves the triple word score open with the X or something. And now in all of your rollouts, a lot of those rollouts, the opponent will be able to play on that triple word score using the X. And so that's what shows up this. That's what gives the big benefit. That's what the Monte Carlo search identifies. It's starting from the current position, and it's exposing the weaknesses of each of the moves that you play, and that comes out in the rollouts. So that's exactly why it's effective. I just wanted to say one more thing, which is technically Scrabble is an imperfect information game. Like, we don't know what's on the opponent's rack. And so far I've completely ignored that part. And Maven completely ignored that as well by doing the most naive thing which you can do, which is just to randomly sample letters for the opponent's rack from the letters that are remaining in the game. And so that's very naive because the opponent actually reveals information about what's on their rack by the way they play, but Maven basically ignored that. But more recent programs have actually made some use of that information. But still, it's playing pretty well already. Okay. So that brings us on to imperfect information games. And I want to talk about some recent work, actually by someone who was sitting in this class the last time around when I gave these lectures. And they're now on the list of success stories in games for RL. And this is an approach called Smooth UCT. So this builds on the Monte Carlo tree search approach that we've seen, but it shows how it can be extended to imperfect information games to get state-of-the-art results and achieve superhuman play in the game of poker. And so the way that this was done is you basically need to consider games, these imperfect information games, where you've got information that needs to be hidden, you've got these states, you need to figure out what your opponent's got, you need to play in a way that doesn't expose your own strategy too badly so you can be exploited. And the approach which was used was inspired by another technique from game theory, which is called fictitious play. And the basic idea was that the agent, when it's doing this self-play, it doesn't just learn how to play against the opponent's current behavior. It learns how to play against all the ways that we've observed the opponent play so far. So it basically averages over all of the opponent's behaviors that we've seen so far, and it learns a best response to the opponent's average behavior, not its current behavior. So this leads to a much more robust approach to reinforcement learning. So let me prefix that by saying that if you naively take Monte Carlo tree search or UCT or one of these methods for sophisticated self-play reinforcement learning approach that we believe works so well in all these other games like Go and so forth, and you apply it to an imperfect information game, it blows up. It doesn't work. It diverges. You don't get to a Nash equilibrium. Okay, but this approach really does find a Nash equilibrium strategy. You can see this when you apply it to small games, small variants of poker. It really does find a Nash equilibrium. So the idea again is basically you see some opponent strategy, you see how your opponents are playing. So you're running these games of self-play, and all you do is you count how your opponent's playing, you count the actions that they take so far, and you remember them. So you basically get an average strategy. You average over all the ways that you've seen the opponent play so far. And that gives you your average strategy. It's just the average of all the things your opponent's done to date. And now, what you do is you mix together a standard UCT algorithm, this basically your Monte Carlo tree search that acts greedily with a little bit of exploration, and you mix that together with something which is behaving optimally against this average policy. So you sometimes behave in a way that's robust against all of the things that you've seen your opponents do so far in your self-play games. And this is enough to stabilize the algorithm because it makes sure that your self-play cycles can't just take you off in some strange oscillation that takes you away from the Nash equilibrium. So the way to think about this in general then, so this is how you build search trees in these imperfect information games, is we need to think about the different players in the game. We need to think that each of the players actually sees different information. And so intuitively, they each have to have their own search tree. Each player basically sees different observations. They see their cards. I see my own cards, so I'm kind of in a different node in this search tree. To player 2, you see some other cards in his search tree. And so what we need to do is build a Monte Carlo tree search approach, or any other tree search approach for that matter, which is able to effectively learn about this set of search trees. And we want to share information amongst these search trees such that basically what we have is each player is picking their actions according to their own search tree, but now those simulations are used to update the statistics in someone else's search tree. So each player is basically figuring out their best way to play from the experience they're observing of other players play during self-play. So we've got this self-play procedure, everyone builds their search tree of everything they've seen so far, and they figure out the best way to play in the context of the simulations they're seeing from everyone else's search trees. So this is the approach which is necessary and effective in imperfect information games. So the idea then is to take this smooth UCT algorithm and apply a smooth UCT search to basically estimate the statistics at every single one of these nodes of this search tree separately. Each player builds their own smooth UCT search, picks actions according to this formula we just saw, and then this approach was actually applied in the computer poker competition last year. And I should mention that in the game of poker, there was a big story maybe about 2 months ago, which came out in Science, which showed that Michael Bowling at the University of Alberta actually came up with a perfect player for computer poker. By perfect, it means that it really, really was so close to the Nash equilibrium solution that you would need like 1 million years of play to be able to differentiate, to tell that it wasn't playing Nash. But it turns out that this very simple agent here, that we've just described using self-play reinforcement learning techniques, actually outperformed the perfect player at the computer poker competition, so outperformed all of the University of Alberta bots. And the way it was able to do this was by exploiting self-play reinforcement learning. So even though it couldn't beat one-to-one this perfect player, it can actually exploit the other players more effectively. And the reason it can exploit those players more effectively is because it's really learning in the presence of self-play. Self-play helps it to see the positions which are interesting as the search progresses. It kind of spends a lot of time considering situations that really can occur when players are learning these different strategies. And so when those play situations then occur in real games, it's already figured out how to deal with them. So it generalizes better, this self-play approach generalizes better to real games against other players than a systematic search as was used by this perfect player, which you can think of as the natural extension of Minimax search to these multiplayer imperfect information games. Okay, sorry, I know that was a lot of information about imperfect information all at once. But any questions about this part before we close? Okay. So I just wanted to conclude by putting up this one slide, which kind of summarizes by going over all of the different games that we've looked at so far: chess, checkers, Othello, backgammon, Scrabble, poker, and asking, well, what's the recipe? What's the recipe for doing well in these games? What was the same about them all? You know, were there similarities? Could we pick out things which were important to be effective? And you know, if you were to go off and try and achieve superhuman performance in one of these games, what would you do? And so this is looking at the best reinforcement learning, or the first best reinforcement learning agent in each case. And we see that the input features in each case, it started off with some input features which were binary. So in chess, we had like, you know, these piece value, these, you know, do I have this piece on the board? Am I in this piece configuration? Do I have this pawn structure? In checkers, we have pieces. In Othello, we have these disk configurations. In backgammon, we have the number of checkers in each position. In Scrabble, we have the, you know, letter configurations on the rack. And in poker, we use these card abstractions, which I didn't really talk about. And then in each case, we built a value function on top of these input features. Most of the examples used a binary linear value function. TD Gammon used a neural network, and I expect to see more work in this direction in the near future. Now we have more effective computational methods for deep learning, and also more stable RL algorithms for deep learning. And then in each case, there was some reinforcement learning algorithm which was applied, either tree-strap, TD leaf, Monte Carlo, TD, and we could think of these as all living in the family of TD lambda. In some sense, we know that Monte Carlo is an instance of, that's TD1, we've got TD0, we've got these minimax variants that use TD leaf and tree-strap, but they're all in the TD family. And then training, we see that this self-play idea, this idea of actually trying to figure out the best way to find the best policy by not training against some fixed opponent, but by training against ourselves and adapting, co-adapting until you arrive at something approximating a Nash equilibrium, has been extremely effective across all these games, as well as being sort of, you know, intellectually appealing. If you can just set this thing off to play itself and then it comes back and beats your expert. And then on top of this, search is crucial. Search is crucial. You need in many of these games to exploit the tactics of those games using alpha-beta search, Monte Carlo search, and some Monte Carlo tree search, different variants of these approaches all put together. I should close by saying, having said that, we should always question our assumptions. So I think I've strongly given the impression and advertised the fact that you know, search is necessary in many games with a lot of tactics. And I, you know, for years wrote these papers saying, well, you know, if you play in a game of Go, it's necessary to use search. You have to search from the current position because you can never build a value function approximator that's expressive enough to capture all the nuances of what happens in this vastly complex game. Except that then we just did that a few months ago, and we built a very deep neural network which was able to play Go immediately just by reading out this neural network, as well as a Monte Carlo tree search with a million simulations. So you should always question your assumptions. It's possible sometimes to do very effectively using the right kind of value function approximation. And there's this well-known trade-off in games, which is between search and knowledge. That you can put in a lot of knowledge into your input features, into your value function by learning, or you can acquire that knowledge through search by searching deeper and deeper and deeper. And these things play off against each other. And there's two ways to make progress, which is to search deeper or to learn better. And I think they're both flip sides of the same coin in some sense. Okay, that's it. So thanks very much for coming to the course, and hope you got something useful about it and continue to do great things with RL. And cheers.